Hello, my name is Cyganowski. I'm from the Laboratory for Soft Bioelectronic Interfaces at EPFL in Switzerland. And we're part of a new Center for Neuroprosthetics where we collaborate with other research groups at our university to develop technologies that help patients whose motor, sensory, and cognitive abilities have been damaged. So when I use the term neuroprosthetics, I mean a device that's designed to either augment or replace a portion of the nervous system. And that can be either the peripheral nerves, the brain, or the spinal cord. So one example of neuroprosthetics that integrate with the peripheral nerve system is bionic limbs for amputees. So these devices aim to restore the patient's movement and the movement control and receive sensory input. So the image here is of a former Marine who was the first woman to receive a bionic limb designed by Northwestern University. At the same time, neuroprosthetics can also help patients with milder damages that still let them have limited control of locomotion. Brain-computer interfaces are a non-invasive type of neuroprosthetic where external electrodes, as you can see with this skull cap, are used to reroute the signals in the brain, particularly those related to movement. So patients who have damaged cognitive abilities can use these devices to control computer avatars, robotic devices, even their own wheelchairs simply by thinking. Brain-computer interfaces can also be used in more general neuropsychology research. The company Nissan is using a combination of neuroprosthetics and simulations to study the behavior of people while driving. Finally, neuroprosthetics can also be used to rehabilitate the spinal cord. And this is really significant since a complete spinal cord injury will lead to devastating paralysis for patients. One of our collaborators at EPFL has shown that with a combination of chemical and electrical stimulation, a rat that was previously paralyzed from a complete spinal cord injury was able to be taught how to be taught to walk again by reestablishing the spinal circuits. So as you can see here, the building block of any of these neuroprosthetic devices I've mentioned are electrodes. And we use electrodes to read or stimulate the neural activity. So one thing we've been exploring in our lab is how to make electrodes softer and more mechanically compliant, which would improve the integration of these electrodes with biological systems. So on the left, you see a microelectrode array that can be used as an interface for in vitro applications, interfacing between cells and tissues. But as you can see, unlike a rigid Utah or Michigan array, this MEA can be fully deformable. We can also use the same technology for in vivo applications, like what you see on the right. This MEA, the soft electrodes are conforming to the sciatic nerve of a rat. So when we design our electrodes, we try to keep four main requirements in mind. First, like I've already mentioned, the electrodes need to be soft in order to be compliant with the surrounding cells and tissues. But in addition, the materials and the processes we choose to fabricate these electrodes also need to be biocompatible, particularly for chronic implant applications. The electrodes should also be mechanically robust to withstand the stresses that it'll undergo and electrically reliable to produce sound recordings and consistent, repeatable stimulation. So now I'd like to elaborate on what I mean by the softness requirements for our electrodes. Here is a scale that shows the elastic modulus of man-made materials compared to the natural materials found in the body. So this is ranging from very stiff silicon and metals, which align with dental enamel, all the way down to hydrogels, which align with the brain, which is the softest tissue in the body. So in our lab, we explore materials that are within the region towards the center, where we're looking for materials that are still soft and compliant, but also friendly in the microfabrication facility. So while in our case we use silicone PDMS, and while this isn't a perfectly ideal material for brain applications, it's not as soft as a hydrogel, it's friendly in the microfab, and it's very well known to be biocompatible. Also, in terms of designing soft electrodes for implants in particular, it's really important to note that the electrodes need to withstand stresses both during the surgical procedure as well as the lifetime of the electrode after it's been implanted. So for instance, if you look at this cross-section of the spine, the highlighted red area is where the MEA would sit, and in this case, it's only experiencing bending. However, once you look at it in the actual application, you'll notice that once it's in the rat, it's going to not just experience bending, but also twisting, stretching, as the rat is curling up, running around, or in the most extreme case, taking its leg and scratching behind its ears. So you can see how important it is to design soft electrodes that can handle all these kinds of scenarios. Excuse me. Now I'm going to show you how we make our soft electrodes using primarily PDMS. This is a general top view image of our electrodes. This all the way on the left is the pad area, which are about 1 millimeter squared. And on the right we have our electrode area. Everything on the top is encapsulated except for the openings of the electrodes, and the electrode area is about 50,000 square microns. So first we use silicon as our carrier substrate. We spin about 100 microns of PDMS. After curing, we take a polyimide shadow mask, and this is actually what we use to define the geometry of our electrode. So this is the top view image of the polyimide shadow mask, and the features on the right side are the pads, and they're about 1 millimeter squared. After this, we deposit metal, approximately 25 nanometers of gold sandwiched in between a few nanometers of titanium on each side for a better adhesion. After this, we peel off the polyimide mask, and we have our electrodes remaining. And then we just set this to the side for our second part. Again, we spin and cure a thick PDMS block. This time it's much thicker than our substrate. It's about 1.5 millimeters thick. We silanize this block to prevent bonding, and the silanization will form a monolayer that gives the PDMS a non-stick surface, which is important for the next step. We spin and cure a thin layer on top. In this case, we wanted our encapsulation layer to be 80 microns thick, so that's the thickness that we used. Then we punch holes where we want our electrodes to be exposed, and the hole puncher has a diameter of about 330 microns. Then we take the first two parts together, and before bonding, we activate the surface with O2 plasma. We align the PDMS block with the electrodes, and then we bond the two together. Finally, we peel off the thick PDMS block, which leaves behind just the encapsulation, which is just what we wanted. And then after we've wired up our electrodes with silver wire, we also end up peeling off the entire PDMS features off of the silicon wafer. So here is an SEM image of the top view of the electrode. The top layer is the PDMS encapsulation with the holes that are exposing the electrode lines underneath. So you can see from this that our alignment is good and our bonding is also good because there's no delamination around the openings. So to test the mechanical robustness of our electrodes, we check the behavior of the impedance as a function of stretching and torsion. So on the left, we have an image of the stretching setup that we've used in the past to determine how our electrodes behave with just stretching. So the MEA is placed between two clamps on each side. There is a silicone ring glued on top of the exposed electrodes, and that's where we place our saline for impedance testing. And on the right is a graph of some of our results of the impedance as a function of electrode strain. And we take this at 3 different frequencies, but in reality we're mostly interested in the 1 kilohertz frequency, since that matches with the frequency of action potentials. So as you can see, in this particular case, our impedance is relatively stable up to an electrode strain of 20%. The impedance in this case is rather high, but if you'll note that these electrode areas are significantly smaller than the ones I've actually mentioned before. So how do our electrodes stretch? They're enabled by a system of microcracks, which you can see in both of these top-down SEM images. So the gold, which is much stiffer than the PDMS, forms a percolating network on the substrate, and as it elongates, the metal twists and deflects away from the PDMS while still being bonded to it. So at the same time, over many cycles, the general morphology of the microcracks changes, and you can see the SEM on the right side. Repeated cycling of the electrodes causes cracking and delamination of the gold film, which actually increases the surface area of the electrodes and allows more contact with the electrolyte. So over time, with repeated cycling, the impedance of the electrodes will slightly decrease. So in order to fully characterize the mechanical robustness of our electrodes, we also must test the impedance during torsion. So first we check the general behavior of the impedance during single progressive torsion. So we go from 1 to 720 degrees at 180 degree intervals. We fix this device, we glue it down to a petri dish, and fill everything with saline to ensure that the electrodes are fully covered, and then clamp the top as we do our progressive torsion. And then we measure the impedance at 1 kilohertz frequency. So these are some preliminary results of the behavior of the impedance as a function of the angle of torsion. So we show 3 electrodes, E1 in green, E2 in red, and E3 in purple. The impedance of the electrodes are in the 20 to 75 kiloohm range, which is pretty similar to the impedance values found in the literature for electrodes of similar sizes. The impedance of E1, which is positioned right in the center of the electrode array, has a relatively stable impedance over the course of the progressive torsion, while the other two have a wider change in the impedance. And this is actually pretty critical due to the positioning of the electrodes compared to the others in the same array. So we believe that this change in the impedance is due to the fact that the electrodes on the perimeter are going to be experiencing not just torsion but also stretching. So just to move along a little bit quickly, we did the same thing, but we did torsion testing over long-term cycling using a similar clamp attachment and a servo motor for torsion. And these were our results. So again, the electrode E1, which is in the center of the array, has the most stable impedance, whereas the other two are influenced by the other stretching components of the strain. So in conclusion, we've shown that the gold metallization on PDMS produces mechanically robust and compliant microelectrodes, but we need to improve our current setup by quantifying the true strain seen by each of the individual electrodes on the array due to the combination of torsion and stretching that occurs. And finally, our goal within the next few months is to test these electrodes in rats in vivo. And our plan is to develop electrodes that last more than 6 months, which takes into consideration the overall lifetime of the rat, as well as the additional stresses that will occur as the rat grows and develops over time. So eventually our aim is for our electrodes to last for decades in the human body to prevent multiple replacement surgeries.